In this video, I will introduce my pico scheduler. It's a Python-based multitask scheduler and can be run on MicroPython and CircuitPython. So this is my GitHub repository. I already set up two Raspberry Pi Pico, one Pico W with the MicroPython firmware, and another one is just the Pico without Wi-Fi, set up with the CircuitPython. And for the MicroPython, I already upload all the scheduler code on the flash storage. Like this one is the scheduler, and this one is some common functions, and the main script here. But this one is scheduler. So for the comment, I only define some time functions, like some sleep and tick microseconds. Oh no, sorry, milliseconds, and the tick difference, tick and tick difference. That function can be will be used in the scheduler. Here is the scheduler. It's a message class, condition class, and task class. Those three are the main classes or objects in the scheduler. I optimize the scheduler with some pre-allocated memory, because in microcontrollers with MicroPython or CircuitPython, if the program frequently allocating objects in the memory, then the memory will have some issues called memory fragments. After that happens, there will be no contiguous memory. There will be no large size contiguous memory left in the memory space. So after that, you may get some like allocating memory failing exceptions. And yeah, this one is the scheduler class. It has a run function, the while true loop. Awesome. In this run function, the scheduler will be schedule tasks to run one task at a time, like a iterator, Python iterator. So in here, it's called the next function to run a function at a time. The function is the task main function. Here is the MicroPython script. In this script, I only define the from top this block is changing the CPU frequency. changing to 240 megahertz. And I define 4 tasks. One is called monitor. Will every task function is a Python iterator, so it uses yield condition. When the function runs at the yield point, then the scheduler will be taken in to check the message and condition in all the tasks, and to select the next running task. And the scheduler will be using the next function here to run the next task's function. And I defined 4 tasks. Monitor, it will be print out. It's not actually print out. It's sending a monitor message here as a message, send it to display. Here is the display function, display task. The display task will be like yield back to scheduler and waiting for the message. If any message available for the display task, then the scheduler will yield back to the display, and the display using the task object to get the message, and then print the message content and release the message. There is the counter function. It's basically just do the counting. Every 100 count, then yield a message to the display. So there are two tasks. Monitor and the counter will be yield out messages to the display task. And LED function, this one just do a LED flash. The interval is in milliseconds, so this one is half seconds. Turn off or turn on the LED on the board. Those one are using to run the second cores, because the MicroPython support to run multi-core. But if you run multi-core, there will have some issues. But I can do it. Here's the main entry, and those print just check the memory left. Here's 3 lines are pre-allocated the memory about the message, condition, and the task. So there will be like 25 messages total, and 25 message objects total, and in total, and 15 condition objects, and 15 task objects. If you have more tasks to run, you can just change those numbers. And it's for the second core scheduler. Already disabled it. So let's just see the first core. Just init scheduler and add task. how the scheduler task function to add a task using the task get from the task global pool get a task object and using the load to initiate the parameters. And we initiate the display task. It will be returned the task ID. The task ID used to send messages from one task to another. And display and edit the monitor task. This was the key value arguments that defined on the function structure, function signature, like this one. This one can be defined all parameters based on your actually need. And here are the counter task. The counter task running interval is 10 milliseconds. It's like 1 second 100 times. And here's the ROD task. Half second per time. And start run the scheduler. Yeah, just like that. If I run this script, you will see the output and the LED flash. It's not an operating system, but it can run some tasks concurrently. It's not parallel, but concurrently. So let's stop it. Those are output messages. The scheduler did static some status like the CPU usage, RAM usage, and here the RAM usage percentage is based on the total RAM as 264 kilobytes. But let's see here, like if you run the MicroPython, the total free memory after you already run the MicroPython, you only left 180 kilobytes. Those are the messages and the conditions left. Condition objects left in the pool. And here are the counter output. Yeah, that's all. Then let's try the CircuitPython. The code here is almost the same. Just the LED definition is not same because the MicroPython and the CircuitPython difference. Here are the CircuitPython definition of the LED. The other thing is the same. There. Yeah. how it flashes. Print the message is normal. But you can see here, if you're using CircuitPython, there will be like less memory left. It's like a total 160 kilobytes. MicroPython have like 20 kilobytes memory more than CircuitPython. The concept here of the scheduler is like you can define more while true loops for your every task, and what you have to do is in your every task, you have to yield back to the scheduler with the condition object every interval. Maybe it depends on your task. You can yield back many times if you have some complex task. You have to ensure that if you run a long time task and not yield back to the scheduler, then the other tasks will be blocked. The scheduler is blocked too. Basically, it's a coroutine scheduler. Every task you write, it's like a coroutine. Actually, that's all. Thanks for watching.